Hello everyone, I'm going to do the bonus question. So the question states if the vectors u1, u2, u3, and r3 are linear independent, then the vectors w1 equals u1 and u2, w2 2u2 minus u3, w3 equals u1 plus u2 plus u3 are also linear independent. So first things first, the definition of linear independence is basically if there exists a non-trivial linear combination of the vectors that equal the zero vector. But if there is a linear combination that exists, then it's linearly dependent, but we want linear independence, so basically no zero scalars essentially. And also, if there's more columns than rows, then it's linear. There's a linear dependence in the system. Otherwise, it's linear independent if there's more rows than columns. But if there's more columns than rows, it's linear dependence. So first things first, we want to start by getting our equations together into a system real quick. So we're given w1 equals u1 plus u2, w2 plus, I'll just write it all out so it's all clearly seen here. So, sorry if my handwriting's messy. So essentially we want to show our linear independence, so we want to show that any combinations of u1, u2, u3 with scalars equals 0 by themselves. And this is like the formal way to do it. So essentially we want the condition to be fulfilled, so that there's non-zero scalar and it's 0. So now we want to sub in our values from u1, all the rest of the equations. Sorry if it gets a bit messy, my handwriting isn't the greatest. And then we got plus c here. And oh boy, it looks very similar, but but the idea should be this. So now we want to simplify this, which you can, so we essentially just multiply it out. This is pretty annoying to do, but to set up our equations, it's kind of necessary. Because essentially we are showing that we want a system to solve, so yeah. So now we factor in order to get a bunch of equations in order to prove that we have a system and that everything's happy and we got our linear independence proven true. So we got this as our first factor for u1. Then we got our second factor for u2. This is just going to be a bit messy because of unfortunately constrained space, but the gist is essentially we're getting our system and setting it up. So now we got, and now like, because if one thing is 0, like that means now we want to prove that a plus c equals 0, a plus 2b plus c equals 0, minus b plus c equals 0. Now we want all these conditions to be fulfilled at the same time, essentially. Since it's we want to prove everything is true simultaneously, so it's non-trivial. So now let's set up our matrix. So this will be pretty, so we got A, B, C. So we got 1, 1 here, 0 for B in the first equation. 1, 2, 1, minus 1, 1, 0. And this is an augmented matrix, but yeah, so essentially we have this. Yeah, sorry if it looks terrible, but it is what it is. So now we want to do row reduction to get this into like row echelon form, so like we can get a definite answer if it's linear dependent, if there's a linear dependence or not. If there isn't, it's linear independence. So here we go. So if row reduction's kind of annoying, it's very easy to make mistakes, but generally speaking, we want to start with one row, get it into the form we want, which we want the staircase format. So we already have start off things. We can do row 2 minus row 1. So we can do this essentially. So now we have 1 minus 1 equals 0. 2 minus 0 is 2. Then we got 1 minus 1 and 1 equals 0 again. So now this will make stuff simpler for us in our system of equations so far, because now we got one row that's like, okay, it's by itself, and now we got this. So now, to make stuff even simpler for us, we can do row 2 times a half. So now we got this. And now we can finish off the other row pretty easily. I'm not going to show the zeros here, but yeah. So now we can just do R3 plus R2. And now we got a very nice system. And now just to make sure we have it all clean and simple, we can do R1 minus R3. So now we have the row echelon form for our matrix. And oh, well, look at that. It's linearly independent. It fits our condition. There's like no zeros anywhere. So we are happy. So A equals 0, P equals 0, C equals 0. Yay, we proved it. So that's the first part of the question done, and now we want to express u1 plus 3u2 minus u3 can be written as a linear combination of w1, w2, w3. And it's like kind of the same idea. We want to set it up into like equations. Then we want to row reduce that because we're doing linear algebra. It's always matrices in the end, I guess. So we got w1. Okay, I'll just write it out now. Let's hope I don't make any mistakes here, because it would be very annoying to re-record this. Sorry about the cough, anyway. So now we got a scalar. Yeah, we want to prove that it's a linear combination of these. Yeah, so we want to prove that there's like scalars exist for this thing to become that thing. And so now, to make this really annoying again, because this is a pretty tedious, so now we want to do the same thing. So we want to plug in our values for the u's. Then we want to simplify that. So now we got this. So we get the value for w again, which is u1 plus u2. And just to make it easier on myself, I'm just going to write it beneath, even though it should be on the same line, but for the sake of simplicity. Oh my gosh, I'm coughing. The math is killing me slowly. So now we got this. And now we want to do some algebra to combine like terms. And then we'll have a system to solve and we'll be happy. Okay. Okay, let's do it. And space is always a problem for me because it's just like... And yeah. Because unfortunately my hands are... I kind of have like a disability with my hands that makes it hard to write out stuff, so... So now we want to factor this, and I think it saves some time. Just do it like this. U1 plus this. Two. So now we got so now we can express the product of u1 plus 3u2 minus u3 as a thing. So we got this, this, this. So now we can prove it's a linear combination of this nonsense. Hopefully no mistakes. And now we want to do an augmented matrix. So x, y, z. So we got 1, 1, 0 equals 1. Just write this all out. 1, 2, 1. Negative 1, 1. And so now we have our matrix, and now it's row reduction again, which is very boring. But we gotta do it, unfortunately, to prove this. So now we should do... Okay, so let's just try to find a row that's easy to do first. I guess we can do the same thing as we did before, which is R2 minus R1, and this time we have to keep in mind that we have more things. Like more variables to keep track of. So now we got... See, now we have 2. Oh, look at that. It's going to be very clean for us to do. Yeah, it gets a bit messy. Because it's like a lot of busy work, but yeah. So now we want to scale R2 into 1. So we just do a half. It should be all 1. So now we can eliminate the third row's negative 1. So R3 plus R2. So we got 0, 1. And that's negative 1 plus 1 is 0. So we got this system, and now we just do R1 minus R3, and we got a row echelon form with the solution 1 and 0. And so that means x equals 1, y equals 1, z equals 0. And it's a consistent thing because otherwise it would be the other way around, like 0. Yeah. So now we got scalars that prove that u1 plus 3u2 minus u3 equals 1 times w1 plus 1 times w2 plus 0 w3, and so that equals just w1 plus w2, which I think would probably be the easiest way to show. Yeah, we can check our answer now. So we got okay, just having trouble remembering the values. So we got this. So now we want to add this to W2. And look at that, it's black magic. Wow, we got the system, and it's just as we predicted. Thank you, row reduction. So yeah. So yeah, this is how you prove these sort of problems. So essentially, it just boils down to like doing the algebra first and getting the proper equations to express what you want. Because that's like the tricky part. Because row reduction is like easy to do, but like the initial setup for solving these problems is all linear. Like you want to show. Okay, yeah, we have the thing. Anyways, hope you guys like this video. I'm not very good at this, but I tried my best, so thank you. Thanks for watching. Please give me a good grade.